recording. Right, so we're going to be talking about the energy conservation model. And so what that is just like how we were talking about, well, we talked about models at the very beginning, what they are. It's basically just a system of ideas that will let us understand the world around us a little bit better, and this system of ideas we're going to talk about today is the idea of energy conservation. So before we can actually talk about energy conservation, let's first talk about systems. Not systems of ideas, I mean physical systems here. So for now, we're going to be more or less done with computing work done on individual objects. My mic sounds weird, or I didn't mute everyone. Let me try a different mic. Is this mic better? Better or worse? Okay, that's weird. I just changed mics from my headset mic to my, oh, you know what? It could have also been using my tablet mic. Anyway, well, let's use this one. So we're more or less done computing the work on individual objects from individual forces. And so we're going to kind of generalize. We're going to zoom out a little bit. So one question that you might ask is, how do you know which force in a third law pair to use when computing work? Now, what I mean by that is simple. When you compute work, you need to know the force and the path traveled. Which force do you use? Do you use the force on the object or by the object? And I hope most of you guys are fairly comfortable in saying you use the force on the object. And in particular, the path you use is the displacement, or is the path of that same object. So use force on the object and the path of the object. That should be fairly straightforward. And the point being is that if you had chosen the wrong force, you would have gotten the wrong answer. You would get the negative of what you were supposed to get, because the forces are equal in magnitude and opposite in direction. But something to keep in mind is that there is not a third law for work. I.e., if one object exerts a force on another object and thus does work, the second object does not necessarily do the same amount of work on the first object. They'll both do work on each other because they're both exerting forces. That is assuming they're both moving, or they're both free to move, but they're not necessarily equal in magnitude at all. A good example of this is that the work done by the Earth on a falling apple is much larger than the opposite. It's much larger than the work done by the apple on the Earth. Now, one reason for this, hopefully you guys can see it or understand it fairly clearly here, is that the forces exerted are equal in magnitude, right? The Earth exerts some force on the apple, pulling it down, and the force is equal to the mass of the apple times g. The same magnitude of force is the force applied by the apple on the Earth. It gravitationally attracts the Earth and it moves the Earth up a little bit. But so because their forces are the same, you might say, oh, well, then the works are the same. But consider that also the work done also depends on the distance traveled, right? If an object travels further, more work is done. And so the apple falls significantly further than the Earth moves upwards. The Earth moves upwards like 10 to the minus 15 meters. So of course the work is going to be larger. The work done by the Earth on the apple is larger. And that's just because the apple travels further. Right. So in order to keep things straight when talking about work, we're going to introduce the notion of a system. So a system is is a group or collection of objects, or of at least one object, I suppose. This is a technical definition, so I have to write it down. At least one object that we have arbitrarily lumped together. So what I mean by that is let's say that we were considering, I don't know, looking for things around the room, a pen and an elephant, right? They don't have to be touching. I could just call them one system. And then I would consider forces on the system. I would consider the mass of the system. I would consider the location of the system. Even though they're not touching or connected anyway, I can just do that. It's an arbitrary choice, but you need to make that choice. This elephant was very dusty. Similarly, I could have just said just the elephant is the system. And then it's a lot more simple to understand because now you know where the elephant is, what forces are acting on the elephant, and so on. But again, it's just a choice. So we also have to have that the grouping that we, or rather, by declaring a grouping a system, we declare that that group is isolated from other objects. So if the system was this elephant, then I wouldn't be part of that system. It is separate, like I am separate from that system. And so for a system, something can either be inside or outside of a system, right? And further, forces can act on a system. So another example of a system might be me together with, or better example would be me together with all of the air in my lungs, all of the organs inside my body, all of the skin and blood and all that stuff. That, like, I didn't have to consider that a system. I could have considered like my head one system and then the rest of my body not part of that system. The point is that I could have I can call myself a system and then I can examine forces acting on me, and I don't have to worry about, oh, is that force acting on my liver or is it acting on my left ear? Right? It's just a force acting on the system. So once we've established that forces can act on a system, we can also realize that there can be forces acting internal to a system. So when I say that, if I, for example, a good example, I am the system, my heart is part of the system, my heart is beating, it's moving, right? So there's some force causing it to do so, but that is a force internal to the system. And in particular, you'll note that forces internal to the system don't really affect the location of the system. I mean, or the velocity of the system for that matter. And we'll get into why that's the case later. But just keep in mind that there is a meaningful distinction between forces external to the system. That would be, for example, the normal force of the chair I'm sitting in pushing me up. That is a force being applied by the chair on me. And the source of that force is external to the system, and forces internal to the system. My heart beating, me clapping, that's internal to the system, right? Because the contact force is being applied from within the system. So what we can do is we can distinguish, not can we can. We can distinguish work done by the system, by forces internal to the group or its system, and work done external to the system, work done by external forces. So what I mean by that is that we can write the total work done on a system is W1 plus W2 plus ... These are all internal. These are all works due to internal forces. Remember, we can always break up the work done into multiple works done by different forces. Plus W1 plus W2 plus ... external. And we know that the total work is just equal to the change in kinetic energy. So we now have an equation relating the total work done by internal forces and the total work done by external forces and the change in kinetic energy. And so for reasons that I'll discuss in a little bit, we can rearrange this. So we get W1 plus W2 plus ... external equals the change in kinetic energy minus work 1 plus work 2 plus ... internal. So this is a totally valid thing to do. All I've done is I've separated external sources of work and internal sources of work and then just move them around. One reason why you might want to do this, for example, is to put on the left-hand side of your equation things that are external to your group or to your system, right? Whereas on the right-hand side of your equation, you have work done internal to the system, but you also have the velocity or the kinetic energy, which relates to the speed of your object, which is also a property of your system. So maybe you have external things on the left, internal things on the right. That's one way to view this. So let's look at an example. Let's look at a block being pushed along a rough surface. By the way, whenever I say a rough surface, that implies that there's friction. And then further, let's call the block plus the surface. Let's let the combination of those two things be our system. So what are the external forces then? Well, external forces are any forces that come from outside of the system. So if the block is being pushed, so there is some sort of applied force. This is the push. And then there's also gravity, right? Gravity is being sourced from the Earth, and the Earth is not part of our system. So these would both result in external work, possibly. In our case, gravity probably isn't going to do any work because it's not moving downwards. Let's look at the internal forces. So there's the normal force. That is a force from the surface to the block. So that's a force from within the system to another object in the system. And friction. Friction is also from the surface on the block and vice versa, and these will produce internal works. By the way, when I say works, I'm just saying that there's perhaps one work for every force. It's not like you have 5 works and 5 works is greater than 4 works. It's just like you can split it up into multiple different types of work. So this is what I mean so the work done by the normal force and the frictional force, those would go on the right-hand side, and the work done by gravity and the applied pushing force, those would go on the left-hand side. Just a quick note, in the future, we almost always make Earth internal to the system. The reason for this is so that we can have gravity be on the right-hand side of our equation. So that gravity is an internal work. We don't have to do this. It just makes it conceptually a little bit simpler. Because if the Earth was external to our system, then we would have to worry about the force of gravity on our system being an external work, and it's relatively straightforward to understand it as an internal work, so that's what we're going to do. And so gravitational work will show up on the right-hand side. So let's now talk about total mechanical potential and thermal energy. So total mechanical energy, potential energy, and thermal energy. I know the comma separation can be a little bit confusing, so that's what I mean. I don't mean total mechanical potential energy. So far we've seen kinetic energy. And so you might say, okay, well, that can't be it, right? That can't be the only type of energy. And so you might say that there should be other types of energy. And you'd be right. The other energies are defined by work done by internal forces. So in a sense, kinetic energy is special. It's not the result of any work. It's not the result of any force, rather. It's just a property that an object has. It doesn't have to do with any forces being applied to it. And every other energy every other energy has some force that's associated with it. That's not quite true. If you start thinking about special relativity, which is this whole business of objects moving near the speed of light, there's another type of energy called rest energy, and that is the energy that an object just has by having mass, but that's a completely separate thing, and we're not going to talk about that in this quarter. That shows up in 9D, so take it if you're interested. Just a quick summary of what we've talked about so far. And this includes stuff from last week as well. Work done on a system. Before we were just talking about work done on an object, but we've broadened that scope to mean a system. Work done on a system by external forces changes the energy in the system. So what does that mean in our context? Well, we know that work done external to a system can change the kinetic energy. But as we've now written, we can see that the work done by external forces can change the kinetic energy, or it could change these works done by internal forces, which are going to show to be another type of energy that a system has. There are three types of energy, or three types of energy changes that can occur within a system. So one is kinetic energy. This is from motion of objects in the system. So they can be moving about within the system. For example, think of like the Earth orbiting the sun. If you consider the Earth and the sun to be our system, the Earth has some kinetic energy, even though it's not really, even though the whole system isn't moving. It's just one part of the system is moving. Also, we could have changes, or we could have changes from work done within the system by conservative force, or by conservative forces. And then same as above, but with non-conservative forces. So we had already broken up forces into conservative and non-conservative forces. And so we see that there are three different ways that we could decompose this right-hand side of this equation. It could be a change in kinetic energy, it could be a work done from conservative forces internally, or a work done from non-conservative forces internally. And so let's rewrite our formula. We have W1 plus W2 plus ... These are all external, equals the change in kinetic energy of components of our system, so that'd be delta KE1 plus delta KE2 for different objects in our system, minus W1 plus W2 plus ... And these are for conservative forces. Oh, I'm gonna run out of room. Minus W1 plus W2 plus ... non-conservative. And these are both internal forces, or internal works. So now so there are three different terms, and that was the point of what I was just making. So just a quick reminder, recall that conservative forces only care about the initial and final positions when computing work. Remember, and I'll scroll up in a minute just to show you. Let me scroll up and show you what I mean by that. Let's go back and look at, say, gravity, which is a conservative force. The gravitational force only cares about the change in position. So that is the final position minus the initial position, i.e. it doesn't matter what path you took to get there, it just matters where did you start and where did you end. Similarly for the elastic force, that's also conservative and also only depends on the initial and final position, or initial and final displacement of the spring. And again, we'll go into more detail about that later. So what we can do is we can define potential energy, which is a new type of energy that you may have seen before in high school, can be defined as a quantity of energy that a system possesses due to its position. So why might we define potential energy this way? So we want to somehow give names to these types of these new types of energies. We have a change in kinetic energy here. We have some type of conservative work here, kinetic energy here, conservative work here, and then non-conservative work here. We want to give names to those. So potential energy would reasonably be the thing that is related to conservative work, or work done by conservative forces. And the reason for that is that we could describe the work done by conservative forces as just some initial or some final value of something minus some initial value of something, because the work done only cares about the final and the initial positions. And so as long as those somethings, the final something and the initial something, only depend on position, then we're good. It's described by a conservative force. So let me be a little bit more explicit here. So the change of potential energy is, and now we have to introduce a minus sign, unfortunately, it's the negative of the work done by the conservative force. So in equations, the change in potential energy equals the potential energy at some position B minus the potential energy at some position A. And that's just equal to negative of the work from A to B, which is a conservative, a work done by a conservative force. So the whole point here is that this delta PE, think of it as something like mg delta y. And we will get into more explicit things in a minute, but the work done by gravity is just negative mg delta y. So if all we're doing is we're sticking a negative sign in front of that, and now we see that we could write mg delta y as mg yb minus mg ya. And then we just say, oh, well, the potential energy at point B is just m times g times the position at point B, and potential energy at point A is just mg times the height at point A. And so in that sense, the potential energy only depends on the position that the object is at. It doesn't depend on how fast it's going or what path is taken. It just depends on where it is. And then you subtract the final minus initial, and you get the change in potential energy, which is the negative of the work. And again, I will be far more explicit about that in a minute, but that's the basic gist. That's why we use this definition of potential energy. So a consequence of this definition, let me zoom out just a smidge. A consequence of this is that there is a force, or there is a form of potential energy, whether it's gravitational or spring or whatever. There's a form of potential energy for every conservative force. So that means if there is some conservative force, you could figure out what that potential energy looks like, what the formula for it is. However, there is no potential energy for any non-conservative force. Does that basically mean that non-conservative forces can't have, but yeah, it's precisely that. Yeah, the idea here is that, in fact, one of the ways that you can define a non-conservative force or a conservative force is, it is a force that arises from a potential energy. If there's a potential energy, it has an associated conservative force. If the force doesn't have an associated potential energy, then it is by definition non-conservative. So it's just another useful way to define conservative versus non-conservative forces. But we can still compute work done by non-conservative forces. Work done by non-conservative forces can still be accounted for. We just call them something else. Because remember, the work done by non-conservative forces doesn't just depend on position, it also depends on the path that it takes. The name that we give for work done by non-conservative forces is generally thermal energy, at least in cases that we will see. So what we define then is we define the change in thermal energy of our system to be equal to negative of work 1 plus work 2 plus ... where these are non-conservative internal forces, or works caused by non-conservative internal forces. So we've established everything then. We have our change in kinetic energy, we have our potential energies, and we have our thermal energies. So now we're just going to pull we're going to pull a trick here, and we're going to come up with energy conservation. So now consider everything, our system, to be everything. When I say everything, I mean everything that exists in the universe. Then, what does this formula up top become? The work energy theorem, which is what that formula really is. It's just a rewriting of the work energy theorem. It becomes 0 equals delta KE plus delta PE plus delta E thermal. So, and this is true when the system equals everything. So the reason why the left-hand side becomes 0 should hopefully be fairly straightforward, right? If our system includes everything, then there's nothing external to the system. So there can't be any causes of forces external to the system. And then similarly, the kinetic energy, the potential energy, and the thermal energy of our system account for all of the energy in our system, or all of the energy in the universe. So this is just saying that the total energy in the universe is the total change of the energy in the universe is 0. So something to keep in mind is that there can be simultaneous changes in different potential energies or thermal energies. What I mean by that is just that, like, you can exchange, like, if your gravitational potential energy goes down, it doesn't necessarily have to go to kinetic energy. It could go to thermal energy or something. Like they think of each of these terms, kinetic energy, potential energy, and thermal energies. You could have multiple of each of them, but think of each of them as just like a bucket, and that the total level in the bucket doesn't change. Sorry, if you added up all of the buckets together, the total level wouldn't change. But like you can shift energies, you could shift water level in one bucket to another without going through kinetic energy first. Basically, the energies can interchange with each other. Think, for example, drop it, like you have an object attached to a spring. You hold it up, and it's at rest, and then you let it go. Eventually, it'll start at rest. The spring is compressed. The object will fall, but the spring will start to stretch out, and then it'll come to a stop eventually. I mean, then it'll keep going, but if we just cut it off when it comes to a stop, all of that gravitational energy became spring energy, is the point that I'm making. And so they can exchange with each other. Energies can transform into other types of energies. So unfortunately, there's one more renaming that I have to do. So I will jot that down really quick for you guys. Potential energy and kinetic energy can be exchanged freely, i.e. you can always go back and forth between them. Exchange with each other freely. But that's not true with thermal energy. What I mean by that is that the thermal energy is almost a one-way ticket. You can easily trade potential energy or kinetic energy for thermal energy, but you cannot trade thermal energy for either kinetic or potential energy. It is, quote, a one-way ticket. So that's why we classify thermal energy or potential energy and kinetic energy into one more type of energy. This is mechanical energy. So mechanical energy can always be shifted around inside of itself. And thermal energy, and you can go from mechanical energy to thermal energy, but you can't go back. So all of this business that we've been talking about, in particular this formula up here, all of this is known as a conservation principle. So when I say conservation, it's very closely related to the meaning of the word conservation when you're talking about animal conservation. The idea here is that a conserved quantity, and perhaps this is obvious, let's give that an underline, is a quantity that doesn't change over time. So from this formula up top, we can say that energy might change form, it might move around, but the total never changes. And so I have to give a caveat here because I don't like lying to students. That's not generally true. Like, our universe doesn't actually conserve energy, but it's for a very deep reason. And this equation that we've written up here is true as an approximation in all systems that you'll encounter in this course and in 9B and in 9C, and probably 9D as well. The only place where that fails to be true is when you start thinking about the size of the universe. And that's involved in the study of cosmology, which is the study of the origins and the evolution of our universe. So take that with a grain of salt. Can't you get work from a gas be heated up in a constant pressure environment, turning thermal energy into mechanical energy? So you will learn about that in 9B, but the takeaway here is that heating something up is not thermal energy. Thermal energy is a quantity that a thing has. Heat is the transfer of energy, is the transfer of energy from one object to another. So they're not quite the same. heat can do work, or you can transform heat into work. You cannot transform thermal energy into work. At least you can't transform all of the thermal energy into work. But you'll see that more in 9b. For our case, we're just going to be talking about friction basically as our only form of thermal, or as the only source of thermal energy, and that you can't really transform back into work, right? So the equation that this is pointing to, this equation states that a system, I didn't stay on the line, a system with no external work no external work done on it. By the way, when a system has no external work done on it, we might call it a closed system. Conserves energy, i.e. the total change is 0. So one way to understand this business of the universe not actually conserving energy is that our universe isn't a closed system. At least if you don't consider the space, or if you don't consider space-time being part of your universe, if it's just the background. So this whole business of closed systems is useful because then we can talk about submodels for energy conservation. So for example, if a problem says something like there's no drag or friction, what that tells us is that the change in thermal energy is 0. And what that implies is that the change in kinetic energy plus the change in potential energy, and by the way, this only applies for closed systems. If you have a closed system with no drag or friction, then that would imply that the mechanical energy is conserved. Which means, yeah, if the change in mechanical energy is 0, then the mechanical energy is conserved. Similarly, if I said you had a closed system in which an elastic collision took place, that would imply that the change in thermal energy is equal to the change in potential energy, which is just 0, which tells us that the change in kinetic energy is 0, i.e. kinetic energy is conserved. So these are closed systems. Of course, if it's not a closed system, that just means the left-hand side of these equations aren't necessarily 0, which means that, of course, the kinetic energy or the mechanical energy is not conserved. So these are just, they're just some hints that you get, or maybe not hints, keywords that you'll learn to see in physics that correspond to certain subcategories of for energy conservation. And this whole business of frictionless or dragless environments or elastic collisions, those are just submodels of the energy conservation model. Right, so I promised that I would get more explicit when talking about potential energy. So let's do that. Let's talk about the potential energy function, because so far we haven't actually done any calculations for gravity. So in general, it's easier to handle numbers than it is to handle forces and integrals, right? Meaning, if I could give you a function that you plug in a position and it spits out a potential energy, it would be much, much easier to just find the difference in potential energy by just subtracting one number from another, as opposed to having to take the force of the gravity and integrate it along a path and then use that to compute the change in potential energy based off of the definition given by the negative of the work. So what we can do is we can just, let's go up to where we define potential energy. We can just write a formula for that quantity as a function of position for each given, for all the different forces. Now, this isn't going to do it for every force that you'll ever come across because, you know, there's a lot of them, but we can at least come up with a potential energy function for the more common ones. First, we're going to start with gravity. But we're gonna talk about the elastic potential energy function as well. So let's recall that the force, or that the work done by gravity from point A to B is negative mg delta y, where delta y is the height at position B minus the height at position A. I say recall because we talked about that last lecture, I believe. That was in this whole business. We have here, right? This is the work done by gravity. In this example here, the block sliding in a frictionless loop-de-loop. And we got negative mg delta y. Right, so we should have that the potential energy due to gravity, or the gravitational potential energy, I might call PE sub g, is just the positive mg delta y, right? That's how we've defined the change in potential energy. It's just the negative of the work done by that force. By the way, the reason we wanted that is so that we could have a plus sign here rather than a minus sign. And it makes our calculations easier. And so then the question is if this is PE, if this is the potential energy due to gravity, the change in the potential energy due to gravity, then we should just be able to find two values that we can subtract from one another to get that change, i.e. there should be a potential energy at point A and a potential energy at point B, and then you can just subtract them to get the change in the potential energy. And whatever that answer turns out to be, it has to be equal to mg delta y. So first, keep in mind that M and G don't change. So that means that the potential energy, come on, there we go. That means that potential energy due to gravity should be a function only of the y value, right? That's the only thing that could cause a change in the potential energy. So what should it be? Well, one might write, well, the potential energy due to gravity as a function of y, maybe we write mg times y. Why? Well, the only constraint that we have on the formula for the potential energy is that it must be true that the change in the potential energy calculated this way by plugging in y of b and plugging in y of a and then subtracting them has to be equal to mg delta y. And that checks out. We have mg yb. So if we were to write delta potential energy from gravity from A to B, I know this is kind of cramped, that would be mg yb minus mg ya. And then we could factor, that would be mg yb minus ya, which would just be mg delta y. And so that checks out. It agrees. So that is a perfectly valid formula for a potential energy due to gravity. However, that's not the only possible answer. If, let's say, that potential energy due to gravity as a function of y was instead m times g times y plus some number, let's call it u naught, then the change in potential energy from A to B, and you don't have to write from A to B every time, I'm just doing it just to make, because you guys are new to this concept, would still be mg delta y. So the point here is that both of these choices of our potential energy function are equally valid, because the only restriction that we have is that the change in the potential energy agrees with what you calculate when you calculate work. And if what you calculate when you compute the work is mg delta y, then both are perfectly fine. So what's the takeaway here? Takeaway is that we can reference the zero potential energy. I'll explain this in a second. The zero potential energy to be anywhere. And things still work out. When I say things still work out, what I mean is that the potential energy still agrees with the work done. And that's all we care about. What that implies is that it's safe to always add a constant. To your potential energy function, that is. Now, you can't add different constants in the same problem because you have to be consistent. But if you just decide to use mgy plus 8 million joules, you're totally allowed to do that. So what the sentence here means is that let's say that we take potential energy due to gravity for an object of mass, say 2 kilograms. Let's just write down the formula, and let's say that y equals 0. Let's say on the floor of my house. So this would be 2 kilograms times 10 meters per second squared times y. So that means that if the object is on the floor, which we're just calling 0, that means that the potential energy of that object is 0. But I didn't have to choose that the position of the floor is where the y value equals 0. I could have chosen the position to be where y equals 0 to be the roof. Then, in that case, where we have the y value for the floor is now, let's say, now it's minus 2 meters. Now, that would mean that the potential energy is what, 40 joules? Negative 40 joules, rather. So the point is that the value of the potential energy depends on where you put your zero point. And so it could either depend on where you put your 0 coordinate value, or it could depend on where you put the 0 energy value. Basically, the point that I'm making is that the value of potential energy for any given position of any given object doesn't actually mean anything, because you could just say that it has 0 potential energy, and then just things have potential energy relative to that, i.e. you can always add a constant so that the potential energy of that particular object at that particular spot is 0. That just affects the potential energy of everything else too. And this will come in handy later, especially in 9C, it comes in handy quite frequently. But we will talk about this a little bit too more in this course. Yeah, the recording is on. Right, so we only have 2 minutes left or so I will just do a very quick example, and then we'll start up next time with another example. But the example that I want to start with is throw a rock vertically, and then catch it at the same height that it was thrown at, and we're going to assume no drag. So remember that assuming no drag means that there's no change in thermal energy. And catch a rock vertically. So no friction means the first thing that we should establish is that no friction means that 0 equals the change in kinetic energy plus the change in potential energy. We're going to assume there's no external forces, hence we have to have the Earth as part of our system. But if there's no external forces, there's only gravity, and now there's no friction, then our left-hand side is 0 because there's no external forces. And then we just have change in kinetic energy and change in potential energy, and no change in thermal energy. And in this case, that potential energy is gravitational potential energy. And let's say that A is the launch point and B is the catch point. So the change in the gravitational potential energy is just mgyb minus mgya. By the way, for a lot of cases, it's safe to just use mgy, but sometimes it'd be more clever to use a different one, like mgy plus something else. So for a lot of cases, we're just going to use this. Now, we've assumed that we're catching the rock at the same height that it was thrown at. So this is mg times yb minus ya, which is just 0 because the vertical position is the same at the initial and final position. So that tells us that the change in kinetic energy is 0. And so what's the formula for kinetic energy? It's 1/2 mv at position B. This is the formula for the change in kinetic energy, sorry. That means that this is 0, which tells us that VA equals VB. That is, that the height that the speed at which the rock left your hand is the same speed that the rock hit your hand with. Note, by the way, that this is not a vector equation. This is an equation of scalars, hence its speed. because VA in this case means the vector or the magnitude of the vector VA. And just a quick note here is that nothing in this calculation changes regardless of whether or not the rock had any initial or final, had any horizontal velocity at all, right? It could have been that I threw a baseball up and over to someone who caught it at the same height that I threw the baseball at. And the point would be is that the initial and final speeds would still be the same because the horizontal direction doesn't the direction of the velocity doesn't matter in these calculations. All that matters is the magnitude. And so if the magnitude of the velocity stays the same, then whether or not you have any horizontal component doesn't matter. All right, so we just ran a minute over, so we'll call it there. We're going to continue next time with more examples, and we're going to talk about the elastic force as well. But